Hello everyone, welcome back. Today I'm going to explain a problem on a design of a post tension girder. Question is, design a post tension girder which is spaced at 2.4 meter center to center and has an effective span of 9 meter. Live load is 3 kilonewton per meter square. Exclusive of self weight, concrete weights 25 kilonewton per meter cube. Permissible compressive stress in the concrete at transfer and working load are 14 Newton per mm square and 12 Newton per mm square respectively. Permissible tension in the concrete at all the stages of loading is 1 Newton per mm square. The loss ratio is 80%. Also, determine the number of 7 mm dia wire required. If the permissible tension in steel is 1000 Newton per mm square, cover required for girder system is 100 mm. Here in this question, they have given this diagram. First of all, it's a post tension girder which is placed at 2.4 mm center to center, means they are talking about these beams. Okay, these are the three beams they have given, and center to center distance between the girder or the beam both are same. The center to center distance is 2.4 meter, 2.4 meter. Next is effective span of 9 meter. Effective span in the sense, understand the difference. Here, whatever you can see this right side diagram, it's just a cross section. Okay, in the cross section, you can see all the three beams. But when you come to this left side diagram, it is not a cross section, it is a longitudinal section. They are telling the length of the girder is 9 meter. On this girder, UDL is acting. Next is live load is 3 kilonewton per meter square. Here you can observe they are clearly given in the question that in the diagram that it is 3 kilonewton per meter square. Exclusive of self weight, concrete weight is 25 kilonewton per meter cube. That is, density of concrete is 25 kilonewton per meter cube. Permissible compressive stress in the concrete at the transfer stage and at the working load is 14 Newton per mm square and 12 Newton per mm square. For the transfer case, it is 14 Newton per mm square. For working load, it is 12 Newton per mm square. Next is a permissible tension in the concrete is 1 Newton per mm square, and this is a loss ratio. They have given the loss ratio in percentage, that is 80%. Determine the number of 7 mm dia wires required. They have given the dia of the wire, that is it's clearly we can see that it's 7 mm dia of the wire. So how, if single wire is of 7 mm, then how many number of wires is required is a question here. Permissible tension in steel is 1000 Newton per mm square, and the cover required for the girder system is 100 mm. This is a details, or these are the data they have given in the question. So let's solve the problem. Before solving the problem, I just wanted to say about this diagram, that is, it's a girder and the center to center distance of the girder or the beam is 2.4 meter, 2.4 meter. Here the UDL is acting at a distance of 1.2 meter from the center to the end. Again, from the center to the end is 1.2 meter, 1.2 meter. UDL is 15 kilonewton per meter square. About this 15 kilonewton per meter square, in question they have not spoken anything, but in the diagram they have given it directly. So while solving the problem, other than question, you should refer or you should check the diagram carefully. A few data will be given in the diagram also. Then it is a live load 3 kilonewton per meter square. Okay, let's start with the solution. That is, given spacing is 2.4 meter. So WQ is live load. So in the question itself, go there. See, for a live load, we require load into its length. Load is 15 kilonewton per meter square. What is the length of this load? Where to what distance it is acting? 1.2 plus 1.2 into 15. So for a live load calculation, WQ equal to 1.2 plus 1.2 into 15, that will give you WQ has 36 kilonewton per meter. Next is a calculation of moment due to live load. MQ is WQ into L square by 8. This is for a simply supported beam carrying a UDL. The formula is bending moment formula is WL square by 8, and this is moment due to live load is equal to, we know the value of WQ 36 into L is the length of the beam, 9 square by 8, where 36 is WQ value, L is length of the span is 9 meter. That will give us 364.5 kilonewton meter. So just convert that it into Newton mm. That will be 364.5 into 10 power 6 Newton mm is a value. Next calculation is for a dead load. Dead load notation is Wg is equal to 3 into 1.2 plus 1.2. Here, go back and see here. Here in the question itself, they have given it as 3 kilonewton per meter square. That is, it's a slab load. Okay, don't get confused. It's a slab load, so you should take this as a dead load. How much slab load is acting at a distance of 1.2 plus 1.2? So take it as a slab load, so it will come under dead load plus self weight of the beam. We already know for a self weight calculation, it is cross section into density, where here important point should be observed here is it is B into H into 25 by 10 power 6. Why it is B into H? In question itself, they have not given anything about either B or H. They have not mentioned anything about those things. So here both are not given in this point. So what we are doing is we are just assuming B value. We cannot assume the we are not assuming the depth. We are assuming its width. So width I'm taking it as, or I'm just assuming it as 300 mm. You can go for 250 also, but don't go beyond 350, 400 and all. So 250 is okay, 300 is okay. I'm just going for a 300 mm. Here substitute 300. After simplification, you will get 7.2 plus 7.5 into 10 power minus 3 into H kilonewton per meter. And why did this 10 power 6 has come here? Because I have just converted mm to meter. Width was in mm. Convert that it into meter. It will be 10 into into 10 power minus 3. H is also in mm. Convert it into meter. It will be H into 10 power minus 3. So my 10 power minus 3 here, 10 power minus 3 here. If we write that in a denominator, it will be 10 power 6. Like that I have simplified it. Next thing is it's about the moment due to dead load. formula for a simply supported beam carrying a UDL is maximum bending moment formula is WL square by 8. As we are dealing with a dead load, we should take a dead load value. So notation is mg and wg here. Wg is known, just copy down here, into 9 square by 8. And by looking at these values, don't get confused. How did I get from 7.2? How did I get 72.9? It is by this simplification. 9 square by 8 will be that is multiplied to this will be 72.9 plus 75.94 into 10 power minus 3 into H kilonewton meter. Convert that it into Newton mm. It will be 72.9 plus 75.94 into 10 power minus 3 H into 10 power 6 Newton mm is a answer. Still depth is unknown. Okay. Next is a condition given. FTT is equal to minus 1 Newton per mm square. It's directly given in the question, as well as for FTW it is minus 1 Newton per mm square. You can check here, they have given permissible tension in the concrete at all stages, whether it's a transfer stage or whether it's a working stage. The value is 1 Newton per mm square. Okay. Because it's a tension, permissible tension, I have considered, or I should take the sign as negative. So minus 1 Newton per mm square. For this also it is minus 1 Newton per mm square. You should be careful with these things. That is tension, it is negative. If tension was not there, it would have been 1 Newton per mm square. You should observe those things in the question. Next is FCT. This is they had clearly given the permissible compressive stress of a concrete or in the concrete at the transverse stages 14 Newton per mm square. So only C stands for compressive stress, T stands for transfer condition. That will be 14 Newton per mm square. FCW, compressive stress in the working load condition, is 12 Newton per mm square. Next is eta, that is loss ratio. Loss ratio in the question they had given it as 80%. So 80 by 100 you will get it as 0.8. Okay, eta is 0.8. Next is, you can observe when it is in a transverse condition, the beam will be like this. At the top it will be tension, at the bottom it will be compression. The diagram is like this. I had mentioned compression here, but I had forgot to mention tension here. Okay. Next is for during the working condition, it is at the top it is compression, at the bottom it is tension. Next is calculation of depth of girder. Till now depth is unknown, that is H value is unknown. We need to find out how much is a depth. Okay, so we are using a section modulus formula. ZB is section modulus at the bottom is equal to MQ plus 1 minus eta into mg whole divided by eta FCT minus FTW. And here also the important thing is, why did we take this ZB when we have ZT also? The thing is, as we provide a reinforcement at the bottom, so we have to take, or we should take it as ZB and ZB formula. And in the next step what we have done is, we have just equated the section modulus of the rectangle to this formula. This is for a rectangle section BD square by 6. It is a section modulus for a rectangle section that should be equated to this side formula, that is right side formula, mq plus 1 minus eta into mg by eta fct minus ftw. Okay, here what are the terms we know means, here we know everything except h. Here also the h is unknown. Other than that, we know b, that is we have assumed the b value. So substitute the value. Mq is 364.5 into 10 power 6 plus 1 minus 0.8 into mg is still mg we have not solved completely because h is unknown. It will be 72.9 plus 75.94 into 10 power minus 3 into h into 10 power 6 whole divided by 0.8 into 14 minus minus into minus 1. Be careful with the signs here. Already we have a negative sign here. From FTW also we have got minus 1. Here for B it is 300 into h square by 6. After solving we will get 50 into h square equal to 379.08 into 10 power 6 plus 15.188 into 10 power minus 3 h by 13.2. Simplification is very important. Be careful with the signs, and while multiplying the values you just be careful. After solving we will get a equation as 660 h square minus 15.188 into 10 power minus 3 h minus 379.08 into 10 power 6 equal to 0. Here you can see the arrangement. In this step, h square, that is the highest power, was the first thing. After that, h term is not there, it's just a constant, and here h is there. It was not in a alignment. Always we should go from a higher order to the lower order while finding out any terms from the equation. So I have just rearranged it from the higher order. H square has come first, next h, next is a constant is equal to 0. Therefore we will get h as 769.46. that I have just rounded it off to 770 mm. Therefore, the dimension or cross section will be 300 mm is a width, depth is 770 mm has a depth. Next calculation is calculation of prestressing force. We know that the standard formula is P equal to A into ZB into F inferior plus ZT into F superior whole divided by ZT plus ZB is a formula. Next is, okay, I will go back here. Here we should check whether we know all the terms for this formula. Here, first of all, nothing is known. A is unknown, ZB, F inferior, F superior, everything is unknown in this problem. Okay, so we should find out the values of these terms. The area is, just now we have calculated the dimension, it is 300 into 770, that will be equal to 231 into 10 power 3 mm square. Next is a calculation of ZT and ZB. Here ZT is equal to ZB is equal to I by Y, where why it is equal, that is ZB and ZT is equal means, first of all the Z stands for section modulus. Section modulus at the top is equal to section modulus at the bottom, because as it is a rectangular section, um, we are taking this condition, that is ZT, section modulus at the top is equal to section modulus at the bottom for a rectangle section. Formula is I by Y. Just now we have calculated what is a cross section, 300 into 770 square by 6. General formula for this is this. Here you take it as 29.645 into 10 power 6 mm cube. Be careful with the units. For area it is mm square. For a section modulus it is mm cube. Next is the calculation of F superior. S superior stands for resultant stress at the top. Formula is FTT minus mg by ZT. FTT is -1 minus mg is still whatever I have got. I have just substituted that h in terms of h into 10 power 6 by ZT. In the next step, in the next step also you would have substituted the h value, that is 770. We have got, you have substituted, like we can substitute that. In the coming step also we can substitute, no problem in that. And ZT is known, h is known, substituted, we will get F superior has -1 minus, after simplification it is -4.43. So at the total F superior is -5.431 Newton per mm square is the answer. Be careful with negative signs, don't forget that. F inferior is, formula is, that is resultant stress at the bottom is 1 by eta into FTW plus mg plus mq whole divided by ZB. 1 by eta is 0.8, that is 80% will be 0.8 into -1 plus 131.37 into 10 power 6 plus 364.5 into 10 power 6 whole divided by 29.645 into 10 power 6 is a substitution. So F superior will be 19.659 Newton per mm square is a answer. A is calculated, ZB, ZT, F inferior, F superior, everything is calculated. Just substitute those values here or in the formula. A is 231 into 10 power 3 into ZB is 29.645 into 10 power 6 into 19.659 is a F inferior plus 29.645 into 10 power 6 into -5.431 is a numerator values whole divided by denominator. Here has ZT and ZB both are same, I have just written it as 2 into 29.645 into 10 power 6. So be careful while substituting the values. P is, therefore the P value is 1642.179 kilonewton is a answer for the pre-stressing force. Next is a calculation of eccentricity. Standard formula for eccentricity is E equal to ZT into ZB into F inferior minus F superior whole divided by A into F superior into ZT plus F inferior into ZB. Substitute the values. 29.645 into 10 power 6 whole square into 19.659 minus of 5.431 whole divided by 231 into 10 power 3 into minus 5.431 plus 19.654 into 29.645 into 10 power 6. Therefore, eccentricity will be 226.29 mm is a eccentricity value. Okay. Next is we should compare whatever value we have got with whatever value has been prescribed in the code book. So you can observe here I have written maximum possible eccentricity. Emax is 285 mm as per the code book. As per the code book has fixed a limit has or eccentricity value can be up to, or maximum possible eccentricity value can be up to 285 mm. So Emax is 285 mm. Let's check our E value. It is 226.29. What is the case? E is less than E max, hence it is okay. Whatever eccentricity we have got, we can use it for the calculation. No problem in that, as it is safe or it is within the limit, prescribed limit. Next is number of 7 mm dia wires. So what is the area? They have just given the dia of a single wire. Like that, how many number of wires should be used? We should calculate. To find out how many number of wires, first thing what we should do is, first we should calculate the area of the single wire. Area of the one wire is pi into 7 square by 4, that is equal to 38.48 mm square. Permissible permissible tension in steel is 1000 Newton per mm square. Prestressing force required is, we have calculated this, we have got it as 1642.179 kilonewton. About the eccentricity value, I have just shown this diagram just to make you understand from where the eccentricity value should be taken. Eccentricity value should be taken from the center of the cable up to the neutral axis. Okay. Next, the final thing is, we know all the values, just we need to substitute it here in this formula. Therefore, the number of wire required is equal to pre-stressing force whole divided by force in each cable. Okay, here there is a spelling mistake. Yes, force in each cable. Fine. Okay. Pre-stressing force value is 1642.179 into 10 power 6 is a value. It was in kilonewton. I have just converted it into Newton. So it is 10 power 3 whole divided by, what is the permissible tension? It is 1000 Newton per mm square. That should be multiplied into the area of one single cable. Okay, so it is 1000 into 38.48. 38.48 is nothing but area of the single wire or the cable. So if we solve this, we will get the number of cables. Here number of cables is, whatever we have got from the calculation is, it is 42.67. that is equal to, that should be made equal to some whole number. I have taken it as 43 Newton. 43 numbers. Don't reduce the cable. So just let it be, make it a whole number. So I have just taken it as 43 numbers. Here it is understood that we should provide 43 number of 7 mm dia wires in order to take the pre-stressing force as 1642.179 kilonewton. Okay, that is a logic here. 43. Numbers of wires which is of 7 dia should be provided or should be taken in order to take the pre-stressing force as 1642 kilonewton. Hope you have understood. Thank you.